Hey guys, so we are discussing the vitamins, and in this video I am going to talk about the vitamin C, D, E and K. But before that I want to discuss about vitamin B9 and B12, that is folate and cobalamine. So let's see. First, so we have seen the B9 and B19. B9 is folate, and it will convert it into the tetrahydrofolic acid THF, a coenzyme for one carbon transfer methylation reaction, and it is important for the synthesis of nitrogenous base in DNA and RNA. That we have also learned while we were discussing about the purine. So let's first see that pathway, that how folate is important in synthesis of purine and pyrimidine. As you can see here, during the pyrimidine de novo synthesis, what will happen? So we have discussed this pathway. This pyrimidine is going to be synthesized from the carbamyl phosphate and aspartate, and carbamyl phosphate will come from the glutamine and carbon dioxide. So what will happen? Glutamine and carbon dioxide will combine and form the carbamyl phosphate by the enzyme carbamyl phosphate synthase 2, and 2 ATP will be used here. Now the aspartate will come and it will form the orotic acid. Now this orotic acid will form UMP, that is uridine monophosphate. Now this UMP will be converted into UDP, and this UDP again will form the cytosine triphosphate plus this UDP. What will happen? This UDP will be converted into deoxyuridyl diphosphate, means ribonucleotide reductase enzyme will act upon and will convert this ribose sugar into deoxyribose sugar, and after that it will convert it into thiamine. So here it is uridine, so uridine monophosphate, what will happen? It will first converted into uridyl diphosphate. This uridine diphosphate is converted into deoxyuridine diphosphate, ribonucleotide reductase enzyme. So ribonucleoreductase enzyme will act upon here, and then it will convert it into DUMP, and after that it will get converted into DTMP, and here our folate will be useful. We have learned one relationship, if you can remember, that uridine can convert into thiamine by just addition of a methyl group, because we have seen that deamination of cysteine will lead to uridine, but deamination of 5-methylcysteine will lead to thiamine. So here we required a methionine, and that methionine we will gain from this this methyl tetrahydroxyfolate will be converted into this dihydroxyfolate, and this methyl group will be used to synthesize this. It is N5 and 10, then again it will convert it into tetrahydroxyfolate, and again it will convert it into this methyl group. Now there is an enzyme, this dihydrofolate reductase enzyme will be inhibited by methotrexate, pyrimethamine and trimethoprim. That's why they all cause the folate deficiency. We know that methotrexate use and trimethoprim use will cause the folate deficiency. So this is the site of mechanism here. This was the use of vitamin B9 in the DNA synthesis pathway. Now, this is also important. This is also important during the formation of amino acids. So let's see how. So first, this methionine will be converted into 5-adenosyl methionine. This again will be converted into 5-adenosyl homocysteine. So this methyl group will be go to anabolic pathway. This again will be converted into homocysteine. Adenine will be released, or adenosine, whatever you want to say. Now this homocysteine will be converted into cysteine, and here B6 means pyridoxine will be useful. So as you can see, homocysteine can convert into cysteine, can convert back to methionine. Here vitamin B9 and B12 will be there. Here vitamin B6 will be important. So how this two will act here we have to see, and the folate trap. So what will happen here, this homocysteine has to convert into methionine, as you can see, methionine by the enzyme methionine synthase. So this methionine synthase, and B12 and B9 both will be useful here. How? So first, this tetrahydrofolate containing methyl group. So this methyl tetrahydrofolate will give this methyl group to this methyl cobalamine, and this methyl cobalamine will give this methyl group to homocysteine, and it will be converted into methionine by the enzyme methionine synthase. So this methylene group originally donated by folate, but via this vitamin B12. Now this methyl tetrahydrofolate will be converted into tetrahydrofolate, and this will again get converted into 5,10-methylene tetrahydrofolate by this enzyme, that is serine hydroxymethyl transferase. So it will transfer methyl group from serine to this folate, and glycine will be formed by the help of this vitamin B6. And again this will be converted into methyl tetrahydrofolate by riboflavin. But what will happen in the B12 deficiency, that this methyl tetrahydrofolate can't get converted into tetrahydrofolate because they can't donate to methyl cobal. It won't be formed, so folate gets trapped here. That's why it is known as folate trap. So now let's see what is written. Said B12 cofactor for methionine synthesis transfers CH2 group as a methyl cobalamine and methyl malonyl CoA mutase, important for DNA synthesis. This B12 is also important for DNA synthesis. And in fatty acid synthesis of odd number of carbon branch chain amino acid, what will happen? This methyl malonyl CoA will be converted into succinyl CoA, and this succinyl CoA either go to TCA cycle or go to heme synthesis pathway. So in B12 deficiency, this methyl malonyl CoA level will be raised. So the basic difference between folate and methionine, this B12 deficiency, is that in B9 folate deficiency, there will be no neurological symptom. So only DNA RNA synthesis will be hampered, and this microcytic megaloblastic anemia hypersegmented polymorphonuclear cell will be there, but no neurological manifestation, and homocysteine level will be raised in both condition, in B12 deficiency as well as in B9 deficiency. But this methylmalonic acid level won't be raised. It will be normal in B9 deficiency, and here it will be raised. So this is the main basic difference, and this two reaction we have to learn about the methionine to cysteine and this UMP to DTMP, and the main difference pathway is this fatty